Let's review what we have learned so far about the Gibbs free energy and how the Gibbs free energy can be determined by combining the entropy and the enthalpy of the reaction or of our system. We have seen cases in which, for example, when you freeze water, you go from liquid to solid. Well, when you freeze water, you are decreasing the entropy, so this is negative, but negative negative makes it positive. And because you need to release some energy to freeze the water, this is exothermic. So we have seen that in the case of freezing water, you could plot, if you plot enthalpy, you could plot a plot like this one in which this is negative. It's exothermic. The products are at a lower energy than the reactants. But if we take into account the entropic factor, we see that it depends on the temperature. In here, the higher the temperature, the higher the effect of entropy is, the louder the voice of entropy is. So in this case, because entropy, the factor makes this positive and we want the negative delta G, the higher the temperature, the higher the temperature, the more positive this factor will be. Therefore, it will make what we call endergonic. Endergonic is a process that has a positive change excuse me, in Gibbs free energy as opposed to exothermic, for example. Also, at the same time, when we are freezing water, you already intuitively know that to freeze water you need to decrease the temperature. So what you're actually doing is decrease the factor of the unfavorable change in entropy so that you can make this change exergonic. So this was the effect of temperature. Changing temperature, we can change the spontaneity of processes. However, what we're going to do in this video is discuss the effect of concentration in spontaneity. And that has a major effect in health science or in life sciences because, as you well know, living systems need to keep a constant temperature, so the systems cannot change spontaneity by changing the temperature, but they can change spontaneity by changing the concentrations. So let's try to understand what is the effect of concentration on spontaneity. And before that, we want to make sure we understand what it means, the Gibbs free energy standard. When there is this symbol up here, it means that we are measuring the Gibbs free energy change standard. Standard means typically 298 Kelvin, pressure 1 atmosphere, and concentrations should be 1 molar. So what does it mean that this change in Gibbs free energy is negative when the Gibbs free energy is standard? It means that if you mix 1 molar, so I'm drawing here a beaker, if you mix 1 molar of reactants and 1 molar of products, you're going to, because if this is negative, it means that the reaction is going to move to the right. It's going to move towards products. In other words, let me postpone this. In other words, it's as if you're trying to compare in a football game, for example, you have 10 players against 10 players. So you're kind of measuring which team is better. Okay, so to make sure that you're doing a fair comparison, the number of players for both teams have to be the same. However, so what happens when you do not work at standard conditions? That is, when the concentrations is not 1 molar for all the reactants and products. Well, in this case, in our beaker, you're mixing 2 molar of reactants and 0.01 molar of products. In this case, for the same reaction, since we already established, if you will, that the 10 players of reactants, if you will, the 1 molar of reactants were better because they were moving the reaction forward, if you increase the concentration of these reactants, this reaction will become more forward. That is a more negative Gibbs free energy. Okay, so this just says, notice that this is not in standard conditions because we're not mixing 1 molar of each. We call this an instant Gibbs free energy because it depends on the concentrations that you're mixing. On the opposite, if let's say that the bad team products, if you have a lot of those players, they may end up winning and overcome how good they are, how good the reactants are. I'm not sure if this metaphor of teams is actually working, but at least, if you will, by Le Chatelier, if you're adding a lot of products, you may turn a reaction that from the standard point of view, from a comparison of 1 molar versus 1 molar, it was product bound. If you add a lot of products, you may make it reactant bound. That is, if you mix in your beaker, my beaker is deteriorating, 0.01 molar of reactants and 2 molar of products. In this case, it may depend on each of the reactions, but in this case, you clearly see that the mixture is going to move towards reactants. So there's clearly a dependence of concentration and instant Gibbs free energy. Notice that what changes is what we call instant Gibbs free energy, not the one with the dot. The standard Gibbs free energy, that does not depend on concentration, because having the dot already implies that there is 1 molar of reactants and 1 molar of products. A fair comparison between the two teams, if you will. So how to establish the dependence of concentration and this instant Gibbs free energy? Well, we are going to use this formula. We do not have time to show it, but if you understand that if at some point, if I mix in my beaker, a certain amount of concentration, and I'm gonna make this up, if it was for the same reaction, so I want to have less of this, so if I mix 0.1 of this, 0.1 molar, and 0.9 molar of this, such that finally I have a delta G non-standard, of course, of 0, and so I mix 1.01 molar of reactants and 0.9, I made these number up, of products, and nothing happens, it means that I have added the concentrations that correspond to equilibrium. In this case, Q is equal to K. So let's use this. If my delta G is 0, then delta G standard RT logarithm of Q. But we said that Q is K, therefore we have K here. We have found an expression that relates standard Gibbs free energy and the equilibrium constant. So this means that when you have a negative Gibbs free energy, in order to obtain a negative, this has to be a positive, larger than 1, a constant, equilibrium constant larger than 1. If you have an equilibrium constant larger than 1, this logarithm is positive. Positive and negative will give you this negative. If you have, on the other hand, an equilibrium constant smaller than 1 will give a logarithm that is negative. Negative and negative is positive. Your delta G standard is positive. Therefore, you have this relationship between standard Gibbs free energy, in other words, a fair comparison between reactants and products, and the equilibrium constant. This slide pretty much is just telling you what we have discussed. It should not come as a surprise, because we have already introduced the equilibrium constant, and a large equilibrium constant means a product bound reaction. You may see this equation, in an exponential form. Hopefully you're familiar with these manipulations. So let's try to understand exactly a little bit more with an exercise what's the main difference between Q, K, delta G with the degree sign, the standard, and without it. Okay, so here we have this reaction, and this reaction tells us that the equilibrium constant is 0.25. Okay, so if we bring this up, RT logarithm of K, if this is 0.25, that means I can already calculate the standard Gibbs free energy. I would just need to plug this into 125, and notice that even though standard means that it's a 298 Kelvin, we can assume that these values are not going to change, so I can put any temperature that I want here. Of course, these calculations may be more or less accurate depending on our level of approximation, or how far we are from 298 Kelvin, or in this case 125 degrees. So if this is lower than 1, it means that delta G standard will be negative. Excuse me, it will be positive. Let's make sure the logarithm of something lower than 1 is negative, negative, and negative will make this positive. So let's see if which answers of these are true. The reaction is product favored. Well, we know for these two numbers that it is not. It's actually reactant favored. So this is reactant favored. The standard Gibbs free energy is less than 0. It is not. It's actually greater than 1. So greater than 1, it also implies greater than 0. I'm sorry. Yes, so this should be actually greater than 0. I apologize. It's positive. We do not know the extent of it, but it's definitely positive. Alright, so with these kind of simple exercises, is just to illustrate, again, I will write it again, this equation that you will see many times, which just shows you, and that's something that happens in living systems. The cells can play with the concentrations of any reactants and products that may exist in the cells, so that the reaction may go forward or backward, as depending on the demands of the cell. So we'll see more of these examples in forthcoming videos.